Okay, yeah, so today we're going to be doing algebra and more specifically recursions and maybe a little bit of states at the end if we have time, but probably it's just going to be recursions. So in general, recursions is like a method where like values in a function or sequence where these values are defined in terms of previously defined values. So we can just say like defined in terms. And yeah, there's a lot of questions where, you can just literally plug it in and then it'll repeat itself and it's periodic. But yeah, so for now, we're not going to really be looking at those. We'll be looking at more complex ways of using recursion. So here we have like a little bit of a warm-up problem. It's kind of classic. So there's a dog and it climbs a flight of 11 stairs, and with each step, he either climbs one stair or two stairs. And how many ways can he climb the entire flight of stairs? So I'll give you guys like half a minute or so to think about this. But essentially, you want to think about like, since we're doing recursion, like how is this each step defined in, or each thing defined in terms of previous moves that he makes. So yeah, I'll give you guys 30 seconds-ish. All right, so for these types of questions, a lot of times just to make like writing it simpler, we can say let's define a function f of n such that this is the number of ways to climb n stairs. Then you can consider like the last step that he takes, right? So we're trying to find f of 11 right now. So for the last step that he takes, there's two cases, right? He either takes one stair for the last step or two stairs. Right. So if he takes one stair or one step for the last one, then he's essentially going from the 10th step to the 11th step, right? So this is just going to be the number of ways that he can get to the 10th step. And then you take one like predetermined step, right? One stair going up, right? So there's f of 10 ways that he can do this when the last step is one stair. And for the other case, if his last step is going up two stairs at a time, then it's going to be essentially equal to f of 9 because he got up to f of 9 in some way, right? He got up to the 9th stair in some way, and then there's a predetermined like two stairs for the last step. So you can say that f of 11 is equal to f of 10 plus f of 9. And this doesn't just apply for the last step, right? This applies for every single step. You can split into two cases. Either it's one step or one stair for the last step, or two stairs for the last step. So for any like f of n, you can say it's equal to f of n minus 1 plus f of n minus 2. And this might look a little bit familiar, right? And this is only for n greater than 2, of course. Yeah, so this looks pretty familiar. It's the Fibonacci sequence recursion. But you also need to check like the first two terms. So you can find that pretty easily. Like how many ways are there to go up to one stair? That's going to be 1. And for two stairs, you either go up one time, like just go 2 at a time and you're there, or you go 1 and 1. So there's 2 ways. And then for the rest of it, you can just, build it up like Fibonacci. So f of 3 would be 1 plus 2, and so on. And then for the n, you're looking for f of 11 and just keep writing it out, and you're going to get f of 11 is equal to 144. All right. Yeah, so in recursions, Fibonacci is going to show up quite a bit just because it's like the most, used recursion and well-known recursion. But yeah, notice how we've been trying to like relate f of 11 or f of n to the previous f's, like f of n minus 1 and f of n minus 2. So yeah, you generally want to build up that relationship. All right, let's look at a quite a bit harder question. This one's from Putnam. but it's pretty old. So we define a selfish set to be a set that has its own cardinality, which means the number of elements as an element in the set. And we want to find the number of subsets of 1 to all the way to n, which are minimal selfish subsets or selfish sets. And that means like these selfish sets have no proper subsets that are also selfish. So this one's a little bit harder. So I'll give you guys like 1.5 minutes to think first. But yeah, again, try to think about like casework and how you can relate to the smaller sets. All right, so that probably wasn't enough time to solve it, of course, but hopefully you guys have some ideas on how to do this. Anyways, let's define like a function or a sequence. Here, let's do a sequence because we did a function for the previous one. But yeah, we have, let's say A of n is what we're trying to find. It's the number of subsets of 1 to all the way to n, which are minimal selfish sets. So let's look at like any minimal selfish subset S. And this is a subset of 1 to n. And then we can look at some cases, right? So a lot of times you can think about what if we think about if like n can be in the set or if it's not in the set, because that often gives us a way to start. And in this case, let's see. So if n is not in the subset, if n is not in S, then S is also a minimal selfish subset of 1 to all the way to n minus 1, right? Because n isn't in it anyways. So essentially, if you're looking at this case, then it's equal to A in n minus 1, just by definition, what we define A as. And then the other case must be like if n is in the set, right? We're like determining that it is in the set. Then, well, first of all, one thing to note is that 1 is definitely not in the set. And the reason that 1 is not in like any minimal selfish set is because like 1 itself as a subset like this satisfies the conditions, right, for a selfish set, since its cardinality is 1 and it is in the set. So if it is in any set, then it's not going to be minimal because it has a subset of 1, right? So 1 is definitely not in the set, and we already know that n must be in the set. So let's just say it looks something like this, although 2 might not be included, of course. But yeah, say -1, n minus, and then n. Although, of course, like none of these have to be included except for the n. But yeah, we can imagine just like deleting this n from the set because we already know it's in it. So we can sort of just like ignore it for a second. And the thing is, if we're deleting an element from the set, right, we also need to subtract all the elements in the set by 1. Because if, let's say, like our original cardinality was like 5, and then we deleted an element n, right, then this cardinality turns into 4. So if we don't subtract 1 from every number here, like let's say 5 was originally in the set somewhere, then the condition that it is a minimal selfish subset or minimal or a selfish set at all will be changed if we don't subtract another one. So yeah, we have to subtract 1 from all the terms. So then our subset becomes something like this, from 1 to n minus 2. Although, like I said, like this n minus 2 doesn't have to be in the subset. It's just the maximum number that could be in this subset now after we've like transformed it a little bit. Yeah. Oh yeah, and one thing to note, like why we can just like delete n like this is also because we know that n is not the determining factor. Like n is not going to be the cardinality of the set or the subset, because if it were, then we would have to have like the whole thing, like 1 all the way to n as the subset, and we cannot include 1. So that's why n is not like a determining thing. So it's not the cardinality. We can just subtract it and not really use it that much. But yeah, anyways, after like transforming it, we notice that this is going to be a of n minus 2. And yeah, so if you have any, like, if you have the number of a n minus 2, then you can basically transform it to get to the point where n is in S. So everything here matches up. And so our final answer for a of n would be like summing up these two cases. So a of n minus 1 plus a of n minus 2. This is again Fibonacci, right? The Fibonacci condition. But we have to check the first two terms, and you can get that a1 is equal to 1 and a2 is also equal to 1, just by like working through it pretty easily. So yeah, our answer is just going to be the nth Fibonacci number. And you can notice how like we split into cases, like to break down the problem into versions of the original problem. That's like a common theme among a lot of recursion problems, is just making it into casework and then into smaller versions of the original problem. All right, yeah, if you have any questions about that one, please ask, because it's a pretty complicated question. But yeah, if not, I'll just be moving on for now. So yeah, the Fibonacci numbers are just one example of recursion. There are a lot of others, and in general, we can use like recursion when a relationship is true for any arbitrary term, right? So here's like one example from a game. So in this picture, there's 3 pegs, so 3 of these sticks, and there's 8 rings here. They're stacked from smallest to largest on the leftmost peg, and on each move, we can remove the top ring, so this ring, and place it on any peg. So we can remove this and put it on here or here, as long as we do not place it on top of a smaller ring. So you can't have something like a small ring and then a big ring on top of that. So how many moves would it take to move all of the rings, all 8 of these, to the rightmost peg? And when you're done, it should look something like this, right? Like it should be from smallest to biggest, from top to bottom, right? Yeah, so I'll give you guys about a minute and a half again to think about this, and then we'll discuss. right, so hopefully that was enough time to get some progress in. So for a lot of these types of questions where you're dealing with like a game or something like that, right? You want to try some smaller cases, try, doing it yourself and working through it. So for example, if instead of like 8, we had 2, then this would be a lot easier, right? So how would we go about this process? If we want to move everything to the rightmost peg, then we would, like, for example, move the smallest one up here, biggest one over there, and then the smallest one on top of it. So then it would be something like that, right? So if let's define a function again. So f of n is what we're trying to find. F of n is number of ways, or the number of moves that it would take to move n rings, all from the leftmost to the rightmost peg. So we have like n of 2 or f of 2 would be equal to, that was 3 steps, I believe. And if let's just try one more small example and see if you can notice like the process that we're sort of going through here. I know it's a little bit messy, but let's see. So if we want to move all of these to the rightmost peg, right? You can also think of it logically. Like we need to get the biggest one to the rightmost spot. And in order to do that, we need to get like the stuff on top of it to the middle spot, right? Or to some spot that is not the bottom, or it's not the right, so that we can move it on eventually over. So first, we're going to like move the small one to here, and then move this middle one here, and then move the small one back on top here. So that way we have like this biggest one over there, and then we can move it to the right spot. And then we go through some process to get these 2 back onto here. So like move the small one over there, move middle one here, and then the small one back on top, and then you're done. So that was a bit messy, but if you do that for a few cases, you'll start to make like some observations, like how I just mentioned that we need to move like everything besides the bottom one into the middle one so that we can move the bottom one to the right, right? But anyways, f of 3 was, I think, 7. Yeah, so if you can make like these types of observations, then you can sort of break this game up into a few different steps. So our first step is, well, we need to move like the non-bottom rings into the middle spot, like the top n-1 rings into the middle. Move top n-1 rings to the middle. Right, and then after you move like the top n-1 rings to the middle, you can move the biggest one to the right. Oops. And then after that, what do you do? Well, you're in a state where you have like n-1 rings that are in order in the middle, and then you have the big one on the right here. So you're just going to move all these ones in the middle to the right. So the top n-1 to the right. Okay. And this is recursion, right? Because remember how we defined our function f of n? It's the number of moves that it would take to move n rings from the leftmost peg to the rightmost peg. But it doesn't really matter that we're saying like leftmost peg to rightmost peg. If you're moving it from the middle peg to rightmost peg, that's the same thing, right? So yeah, if you notice for the first step, like what's the number of ways or the number of moves that it takes to get these n-1 rings to the middle? Well, that's just going to be f of n-1, right? Because you can just ignore the fact that the bottom ring exists, right? Just pretend that doesn't exist. Then all you're doing is moving n-1 rings from here to here in order, right? So this is just going to be f of n-1. So yeah, that's like the important part here. And then the second step is pretty obvious, right? You're just using one move to get the leftmost one to the rightmost one. So that's just like one step. And then lastly, you're moving the top n-1 from the middle to the right. So you're in like this stage right now where you have like 2 things here and 1 here, or in our case, 7 things in the middle and then 1 on the right. And in that case, it's also the same as just moving n-1 rings from one stick or from one peg to the other peg. because this like big one on the right, like it doesn't affect anything because you can place anything on top of it. You can just treat it as part of the board or part of the floor. So this is also f of n minus 1. So overall, you have that f of n is equal to 2 f of n minus 1 plus 1 if you just add everything up. And your answer, f of 8, if you build it up, is going to be 255. You can also notice that it's like 2 to the power of n minus 1, and that's very easy to prove using induction if you use this relationship. But yeah. All right, we have 6-ish minutes, so I think that's enough time to do one more question. So we're not getting to states today. Yeah, so this problem, we have 6 sprinters and they're in a race. So we want to find the number of finishing orders if ties are allowed in the final standings. So this is one example that is allowed. We can have any ties for any place. Yeah, so don't have much time. So I'll give you guys just like half a minute or so to think, and then we'll get started. All right, so like all the questions that, or almost all the questions that we've been doing earlier, we basically want to break down this problem into like some type of case or something, and then make it so that the final answer involves smaller versions of it. So yeah, let's take a look at this. If we have 6 sprinters, let's say that we do like some casework, or not really casework, but like let's just say we have K people, K runners, all tie for first. So we have K people that tie for first place, and there's 6 choose K ways that you can like pick these K people, of course. Then how many ways do we have to finish like filling up these spots, or to finish filling up the final standings? Well, if we have like K people for first, right, then we have 6 minus K people left. And these are filling up like spots from second to last, right? And how many ways are there to do that? Well, actually, let's first like say A of n. A of n is what we're trying to find. It's the number of standings there are for n people in this race. Okay, so when we have 6 minus K people left, and they're filling up the standings from second to last, well, if you think about like very clearly, right, what is the difference between from second to last and like first to second to last? Sorry, like first to last minus 1 place, right? There's like no real difference. You can just imagine them all shifting. So this is exactly like the same condition that we had earlier. Like we're still allowed to have ties and everything else. And essentially the number of ways that we can fill this in is just going to be A of n minus K, or 6 minus K in this case. Let's just say 6 minus K. Right, so then now if we look at like the cases, we're essentially going to say, okay, K can be 1, K can be 2, K can be any number up to K, or up to 6. So then we are going to just sum all of that up. So A of 6 is going to be equal to the sum of from K equals 1 to 6. And then remember to do the 6 choose K part. And then multiplied by A of 6 minus K, because that's the number of ways that we can arrange everyone left over. And from here, you can, of course, you have to first like find a few terms, and then you can just work it out and work up to 6, or yeah. And in general, you also have that A of n is equal to this, n choose K, and then A of n minus K. So yeah. And here, like, because 6 is such a small, like relatively small number, it's not a big deal to actually just, work through it and find what is A0, what is A1, what is A2, and build it up. You don't necessarily have to find the closed form all the time. So like the previous question here, you could find the closed form pretty easily, and you can solve this for, whatever n is. But in this case, it's a lot harder to find the closed form. So you don't necessarily have to do that. You can just work through it. So the important part is like you get the first few terms at least. So A0 is equal to 1. Of course, if you have 0 people participating, there's one way that the standings could look like. Then A1 is also 1. And then from there, if you wanted to like work through this, for example, we could have 6 choose 1 times A1. Or sorry, we're not using 6 in this case because we're looking at 2. So 2 choose 1. Yeah, and then plus 2 choose 0, or 2 choose 2 times A0. And then that would give you 3. So if you plug these in, and you can use this sort of method to build all the way up to 6, then you'll finally get that A6 is equal to this. But yeah, you can work through this problem again on your own later. But that's it for today. If you have any questions, feel free to message it in the chat. And if not, then just thanks for coming.